In part 1 of this video, we established that when market crashes, it triggers massive liquidation waves, like the $429 million liquidated in a single week on Aave. When these liquidations occur, liquidators collect instantly between 5 to 10% of these amounts as bonuses. But here is the brutal reality. You can't do this manually because you are competing with bots. And even if you have a bot and your bot depends on polling RPC every 30 seconds, or your code or your architecture is not well optimized, you will be beaten to every single payout. If you are new around here, my name is Abolaji, and I welcome you to Syncedge Solutions. Today, we are going to be coding liquidation bots that has high probability of consistently capturing liquidations on high margin collateral like Coinbase Bitcoin and wrapped Ethereum. We are going to be designing the architecture together, and it's going to be optimized for speed, capital efficiency, and for zero gas off-chain evaluation. Now is the time for me to keep my commitment to you that every time you see my video, you're going to learn something new. So open your PC, pull your chair, and code along. And I promise you, this will be the most comprehensive liquidation bot video you've ever watched. Just to give you an overview, our production grade liquidation bots will be able to work on any EVM compatible blockchain out there. But just for this tutorial, we'll be testing it on base mainnet fork. We'll be using Aave V3 for debt liquidation. We'll be using Uniswap V4 for flash accounting swaps. We'll be using Balancer V2 for capital because we'll be able to take free flash loans from it. We'll also be using Chainlink Runtime Environment. So Chainlink Runtime Environment help us to scan thousands of health factors off-chain for zero gas cost. Then after we'll see liquidation opportunity, then we'll fire and call our liquidation bots. Before we dive in, please don't forget to like, share, subscribe, and pin the notification bell so that you get notified of our subsequent videos. Also do well to check out syncedgesolutions.xyz/bots. You'll be able to see our other DeFi bots and you can reach us to us on any of them. We also have our Telegram group, but before you can join our Telegram group, you would have to deploy your own pivot bot first. So go to syncedgesolutions.xyz/pivots, then you'll be able to deploy your own pivot bot. It costs nothing except gas fees. And once you do that, you'll be able to earn leverage yield on your leverage open position. Before we delve into the architecture, let me show you what our bots, our liquidation bots behavior will be like at the end of this tutorial. So I have two terminals open here. One, I'm running make Anvil, which is base mainnet fork. I'm running it locally. So the second terminal will be for us to run our commands. So I'm going to deploy our bot first. This will be make deploy or local. This will deploy our bots. So we have the two main contracts, and you are going to see that this is the engine liquidation executor deployed here and liquidation watchlist deployed here. All right. So the next thing, open a position. We are going to open a position on Aave V3. I'm going to run make end-to-end create position. So this will open a position with collateral. It will deposit a collateral of wrapped Ethereum. As you can see here, one wrapped Ethereum, and he has borrowed 500 USDC Ethereum. The current ETH factor is 3.2, so it's safe. So to make this liquidatable, we are going to crash the price. So I'm going to run another command now, make crash oracle. Oh, this is make A to E crash oracle. Crash. Yes. So we are crashing the price now. Okay, so we have the price. Let me show you the price now. This 1932 is the current price of Ethereum, but we've crashed the Oracle price on Aave. So the price Aave will be seeing is 500 US dollars. So one wrapped Ethereum goes for 500 USDC. So that's what we've played around here to crash the price. So you would see the Earth factor has changed from 3.2, it has dropped to 0.8. All right. So now that makes this position liquidatable because it's 0.8. Now I'm going to now liquidate the position with our bot. Now I'm going to run E2E dash liquidate. Yeah. And let's see. Let's look at the final log. So we can see the debt before was 500 USDC. The debt after we have liquidated is now zero. Our profit is 0.74 wrapped Ethereum and it's been transferred to our wallet. That's why our bot, which is the liquidation executor, has zero balance. Now, all of this will make more sense by the time we go through the architecture, but I just want you to see what the basic behavior of our liquidation bots. Let's now look at the architecture. So you can see this is the architecture. I'm going to zoom in. Let me just move myself to one side here. I'm going to zoom in now. Okay. So basically our liquidation bots will have two main smart contracts. We'll have liquidation executor smart contract, and we're going to have liquidation watch list. So this is the engine, the executor, and it's going to be interacting with our balancer V2 for flash loan. It's going to be interacting with Uniswap V4 for swap. It's going to also be interacting with Aave V3, and this is where our debt liquidation will be taking place. Then we are going to have this our second smart contract will basically be for storage. You can see our watch list, our borrowers that we think are in danger of liquidation, the borrowers that we want to be watching. We are going to be storing them here, and we'll be using our backend script update watch list. It's going to be scanning for borrowers whose health factor is close to 1. So it's going to be doing that by interacting with Aave V3 subgraph. Subgraph is basically an indexer. Indexer just reflects the state of your smart contracts on the blockchain. So active borrowers, because you have people who have borrowed before and that they've paid off their debts, these are not active borrowers. We are only interested in active borrowers and those that their health factor is close to 1. So this is what our script will be fetching for us by interacting with our V3 subgraph. Then it's going to now update the liquidation watch list with those borrowers. Then we have our chain link side of things. This is where the Chainlink Runtime Environment will be. This is basically for automation, as I said. So, and our runtime environment will also be monitoring the price as it changes. So, as the price changes, it will be looking at all the borrowers on the watch list and search for borrowers whose health factor has dropped below 1. And once it finds one, once it finds a borrower who is liquidatable, it's just going to fire and call our trigger liquidation function on the liquidation executor smart contract. So let's look at an hypothetical case of a borrower whose bad loan has a collateral of Coinbase Bitcoin, and he has borrowed USDC. So it's a bad loan because its health factor is less than 1. So let's follow that through and understand how this architecture works. Let's say we have a bad loan, a loan that the health factor is less than 1, and we are going to liquidate it because this is the opportunity we've been looking for. Now, the first thing is this trigger liquidation function will be called. Now, all the terminologies I'm calling, if there's anyone you don't understand, it means that you've not watched the part one of this video. So you can pause this video right now, and the link to the part one of this video is popping up right now. Please click and watch. Then you can come back. Now, when this function is called, the first thing is going to get capital from balancer V2. It's going to take flash loan from it. Now, the flash loan will be in wrapped Ethereum because wrapped Ethereum, there's sufficient liquidity for wrapped Ethereum. So we're going to take that. We now have a capital to go and liquidate the borrowed loan. So over here, the next thing is with wrapped Ethereum, we are going to swap it to USDC. And the reason we are doing that is the bad loan we want to liquidate, the borrowed token is USDC. So we need to change our wrapped Ethereum to USDC so that we can repay it. So we swap to USDC, then we now come to Aave V3. Now, Aave V3 has a unique feature in the sense that with the bad loan, of course, the health factor is less than 1. Now, if the health factor is between 0.95 and 1, we'll only be able to liquidate 50% of the collateral. All right. Now, if the health factor is less than 0.95, then we'll be able to liquidate 100% all of the collateral. So, whichever one it is, we are going to get the liquidation bonus for this token. For wrapped Ethereum, it's usually around 8% or 10%. So, we are going to be handed over the collateral with liquidation bonus, and the collateral is Coinbase Bitcoin. Now, when we have Coinbase Bitcoin, we need to quickly swap it to wrapped Ethereum. The reason we are doing that is the flash loan we took is in wrapped Ethereum and we have to pay back immediately. So we need to swap to wrapped Ethereum. And when we get our wrapped Ethereum, of course, we are going to keep our 10% bonus. Then the remaining amount, we'll use it to pay the balancer V2 flash loan back. So we've just made our 10% bonus. Yeah, you can always configure your bot to send it to your wallet or keep it here, but um, for safety, it's better you send it to your wallet. Now, what we've described so far is the execution part of the liquidation bot. So let's look at the part in which we have to be searching for opportunities like this, and it has to be automated so that we are the first to liquidate the loan. That's when we can make money. If you're not the first, you won't make anything. So it starts with our update watch list script on the back end. It's going to be written in TypeScript. So what it does is to be looking at our Aave V3 subgraph and to be fetching all borrowers with active loans, all active borrowers that still have open positions. We'll fetch them. Then we'll now filter based on their health factor. So the ones with health factor close to 1, you can set your threshold to be 1.2. I think we'll be using around 1.15. Then those ones are the ones close to 1, and these are the ones we need to monitor because any drop in price, it will affect them. So we'll now all those borrowers will be we'll be keeping them in our update watch list, in our liquidation watch list smart contract. So we'll keep all those borrowers that are in danger of liquidation, we'll keep them here and we'll keep monitoring. Now, the next thing is we'll have our Chainlink. The Chainlink environment will be monitoring our data feed. That means the prices of tokens like ETH USDC, Bitcoin USDC, USDC USD, and maybe USDT USD. So these peers will be watching them and be seeing. And anytime we have updated price, we will scan through all of our borrowers here and see the one that their health factor has been affected. So once we see the one that their health factor drops below 1, then our keeper bots here in our Chainlink Runtime Environment will just trigger and call this function for us. So that's what we'll be doing. We'll be doing a lot of scanning here, and that's why it's quite important that this is off chain. Otherwise, every of the scan we'll be doing will cost a whole lot. But because we are running off chain, we'll pay nothing, and we only pay when it gets triggered. All right, so that's why we are using this. We'll be calling this function get all to fetch all of our borrowers that we are monitoring. So this is the overview of the architecture. Let me move myself out of the way again so you can see it appears complicated, but you can see it's simple. So the next thing is for us to jump into the IDE and get started. Now here is my IDE. I'm using VS Code. Any IDE you're using, once you're comfortable with it, you can follow along. And if you don't have any IDE at all, a video is popping up right now. You can pause this video, go and watch that, do your setup, and come back and join us. I promise you we'll be here waiting for you. So let's get started. I'm going to create a folder with this command, make directory liquidation bots inside this folder, and that's where we are going to build our project. I'm going to press enter now. Yes, the folder has been created, which is this. So we are going to open that. Just going to come here, let me right click, new window, close this. Now I've opened a new window. So I'm going to bring up my terminal now with Command J. Command J is for Mac. I think it should be Control J for Windows. All right. So you can see our folder is empty. Now in this directory, I'm going to initialize our project by running forge init. So I just pressed enter. Forge init just bootstrap our project for us. You can see we now have all these um, folders. So these are sample. In the script, we have a sample script. Of course, we are not using any of these. So I'm just going to delete them one after the other. I'm going to delete this one too. We're not using it. All right. And the test. Yeah. All right. So let me create a file. I'm going to call it .env example. This is what will describe my environment variables, although we are not using that now. So here, I'm going to now come here and I'm going to create a folder inside source folder. I'm going to create a file rather, and this will be our liquidation executor dot so. This will be the engine of our liquidation bot. So the next thing is, let me just define the contract here. To write a contract, you have to start with the keyword contracts. That's how Solidity is written. We use the name of the file and we put it in a curly bracket, and that's it. All right. Then we are missing some things. We are going to write there. We need to come here and define our Solidity version 0.8.33, and this is the license MIT. All right. Now let's list out the features we need to build in our liquidation executor. The first one will be over here. The first will be we need features for the following. Let me write it like this: functionalities for the following. The first one will be one to obtain and repay flash loan. And so functionality to obtain from and repay flash loan to Balancer V2. Then the second one would be to swap assets or tokens on Uniswap V4 when necessary. Then lastly will be to execute liquidation on Aave V3. So these are the three main functionalities we need. But at some point too, we'll also need, this will also need us integrating Chainlink price feed. But when we get to that bridge, we'll know how to cross it. So these are the three main features we need. Let's start with the first one, which is the flash loan. So the first thing is, for us to interact with Balancer V2 pool, we'll need to install the dependencies. So I'm going to press Command J to bring up my terminal now. Command K should clear my terminal. Yes. So this is the command to install the dependencies, which is forge install balancer -labs / balancer -v2 -monorepo. So I'm pressing enter now and it's installing. All right. Yeah, it's installed already. So you can see the library and you can see our dependency there, balancer. All right. So now let's import the dependencies here. These contracts here. Let's bring them into our projects. So we'll come here and I'm going to import these dependencies here. It's because it's not able to access. We've not defined this at Balancer V2. So I'm going to do that. We are going to come here now. And don't forget, we've imported iVault contracts from iVault, iFlash loan recipients, and ERC20 interface. We are also getting that from Balancer. So I'm going to come here and create a file called remapping. It will help us to define this directory correctly. So I'm going to call it remappings. .txt. That's a text file. Inside the remapping.txt, that's where we are now going to define this. So we'll come to our liquidation executor. You can see all those errors have disappeared because we have defined this. It can now access it. Now, I want to expand the width of this code so that it looks nicer. So I'm going to just paste my prettier from our previous previous projects. So if you come to prettier here, you can see I'm using width 160. So that will be better for this. You can see it has expanded the width and the code looks fine now. If you don't use prettier, you can just ignore this. But yeah, I just like it to be like this. Now, we were getting error before, and it was because of this at Balancer Labs. All right, this contract we are importing, um, our project does not know where to look for. The compiler does not know where to look for to get these ivots. So we needed to tell it what this at Balancer Labs mean. So it's what we came here to define. So if you come to these remappings again, you'd see that we say at Balancer Labs slash V2 means that whenever it sees this, it should go into our library. You can see this lib folder, Balancer V2 dash monorepo. That's this folder. Then go into the package pkg. Then the next one is go into the interface. So this is the interface. Yes, interfaces. So it's just going to take all of this and put it ahead of the remaining stuff here. All right, so that it can access it. So that's the whole essence of the remapping. All right, let's move on. Now, for these liquidation executor to be able to receive flash loan, it has to inherit this interface. So it will be this is, and we'll put the interface here. Now it's showing us error. It's showing us error because whenever we inherit this interface, we must also we must also define this function. You can see it has stopped showing error, and it's because this receive flash loan function is what will be called whenever we request for flash loan. I mean, if you don't understand that, just be patient. As we go along, you'll understand what I mean. Please don't forget to check out our website where you can explore our other services. Just go to syncedgesolutions.xyz. If you click bots tab here, it will take you to the page where our other bots are listed. For example, we have AI enhanced desk snipping bots V3, and this when you click details, you'll be able to see the video demo of this snipping bot. What it does for you is to watch Uniswap V3 and Aerodrome V2 pool for new tokens launch. And when new tokens are launched, it runs 10-point safety check on them to be sure that they are not honeypot tokens, they are not scam tokens. Before, it also uses AI to gauge the sentiment on Twitter before picking these tokens up. So when it buys the tokens based on your configured stop loss level and take profit levels, it will manage your position for you. You can configure as many take profit levels as you want. And yeah, it does that for you. I'm going to come here now and create another function here. I'm going to call it trigger liquidation. Now, basically what this function is going to do is going to request for flash loan and include payload in the request. All right, so it's going to request for flash loan from Balancer V2. Okay, so this is going to send request to Balancer V2, and other instructions we want to put inside there, it will be included in our request. Then Balancer V2 will respond and send by calling These are receive flash loan function. It's going to respond by calling it, and it's going to call it by our instruction. This payload you're seeing here is what will be in the user data. So it's going to call it with our instruction. So here, this function uh, double. So this is going to receive slash loan from balancer V2 and execute liquidation. So execute swap and liquidation. So let me swap and liquidation. Okay, so this gives you the overview of where we are going. So we are going to start including all the parameters we need here now, and our execution will take place here because here we now have the capital, so we can now swap and do the liquidation. Now we need to call balancer V2, but before we call balancer V2, we need to understand that balancer V2 and Uniswap and other protocol we'll be interacting with are deployed contracts on the blockchain. So protocols, you can view them as organizations on the blockchain. So for you to interact with deployed contracts on the blockchain, you need two things. If you have been watching my video, in fact, you'll be completing this with me. You need to interact with deployed contracts, to interact with deployed contracts. You need two things. The first thing is you need ABI and you need contract address. All right. I said you should think of it as an organization on the blockchain. So contract address tells you the location of the contract, of the deployed contract on the blockchain. So that's why the address is important. Now, ABI, think of ABI as something that tells us who we can talk to in the organization. So ABI tells you who the CEO is, who the finance manager is, the offices that you can talk to based on the kind of information you need. So that's the ABI. So together, both of them defines how you can interact with the protocol or the deployed contract. So in the case of balancer V2, this is the vault contract in balancer V2 we need to interact with. So I'm going to hold down the command button and click I vault now so that it takes me to the interface. All right, this interface represents the ABI. At the execution time, is going to compile this down to ABI level. So you can just think of it as high level of ABI. So this is what we actually need. I'm going to search for command F now. Give me flash. Yes, we are searching for flash loan. Yes, this is the function we want to interact with. So we'll be calling this flash loan to get flash loan. So it takes recipient. So recipient is where you want the flash loan to be sent to. Tokens is the token you want to collect the flash loan in, whether you want the loan to be sent in USDC or wrapped Ethereum, or you need many of them. Yeah, the amounts you want. And this is quite important. User data is the instruction we want to send alongside our flash loan. So we want to use the flash loan to liquidate. So we need to include instructions regarding liquidation here. All right. So let's go back here and let's continue. Over here. Now, to make it easy, of course, I've written this before. So instead of me writing an external function here, I'm going to put an internal function here just to make it a lot more easier, and you would see as you progress. We are going to call the internal function here. Now, if you don't know the difference between external and internal, Now, external functions are functions that outside of the smart contract we can call it. So you can call it with your wallet, or if you have another contract, you can call this contract and call this function from it. But internal functions are only available to be called inside this contract itself. So you can see what I've just done. The name of this internal function, I've put it inside this external function because only the functions inside this contract can call this internal function. That's why it's internal. So we're going to be including a lot of things inside here. That's why I want to create an internal function to put all the instructions, all the code in, and make this a lot clearer. That's just it. Let's come down here and we are going to call balancer V2 here. Now you remember when we saw the interface, the balancer V2 interface we needed to call, its requests. The first thing is the address that will be taking the address that is going to be taking the flash loan from us, and address this talks about this contract we are writing. We want it to be sent there, and it must also be capable of receiving the flash loan. That's why you need to wrap it around flash loan recipients that we brought in here. So we need to wrap it around it. Tokens, we need to define tokens. We need to define the amount, and this encoded is our message. Now let's start with this vault contract first, because you can see I've not defined it. I'm going to come up here now and define this state variable, vault contract. And I define it as immutable. Immutable because it's going to take okay, I've not even defined our constructor. So constructor, I'm going to come here and define our constructor. Now constructor is a function, although arguably that is not callable in the contract, but it gets executed at the time of deployment of this contract. So when I'm deploying this contract on the blockchain now, this constructor, all the code inside this constructor will get executed once, and they can never be executed again. All right. So these are vault contracts. Will initialize it inside this vault, inside this constructor. Is going to be taking, yeah, is going to be taking, you can see autocorrect is even autocomplete rather is even completing it for me. So we'll, as I said, for this vault contract to be complete, it needs the interface or the ABI and the address. So it has to be taken. So we'll have to pass in the address of this balancer vault. I need to call it balancer vault, this variable. Now when we have this variable, it has to come inside here. So the address of balancer V2 and the interface of the vault contract in balancer V2 together gives us the vault contract that we can call the flash loan function on it. All right. So we've defined vault contract and initialize it. Then let's move to other variables here. Now I'm going to define another immutable variable here, and it's going to be the address of our balancer. Now, because again, as I said, I've written it before, I know we will also need the address in future. So this immutable variable will be holding our, it will be holding in the constructor, it's going to be holding the balancer address that we are passing in. All right, now you need to understand something about immutable variables. Immutable variables are not stored in the storage, they are stored in these contracts, in the byte code of this contract. Now it's more gas efficient because all these values, once they are initialized in the constructor, Now you can see the agents tab here that we didn't have before. And what we have here, before you be able to see all of this, you must have deployed your own agent vaults. So what does this do? It helps you to watch over your health factor. It watches over your position for you. And if your health factor drops below a position you have configured, and that you must have configured it over here. I'm using 1.25 for my own. So if it drops below 1.25, it's going to automatically close my position for me. All right. So the agent vaults, this is it's a subscription based and it's fully on chain. Besides guarding your position, it also helps you to deploy different strategy based on your sentiment of the market. So a good example is that if you come to this strategy intent panel here, you can tell you can see whether you are delta neutral or you are bullish on the market, or you think the market will go down, which is delta short. So now I'm feeling bearish. I want to short the market. So if I click here now and I say my target APY, because that's one of the good things about about pivot bots. Instead of paying funding rates on other trading platform, with pivot bots, you'll be earning yield on your open position, as you saw earlier. So let's say my target is maybe 50%. All right. Delta shots. Let's say my risk tolerance is moderate, and I click analyze. So you can see the strategy is giving me. So I can supply USDC and borrow VF against it. And I use about 3.5x leverage and 15.8 APY. I'll get up to 15.8% APY. All right. So at this point, so the top three strategy I can deploy is going to give me there's 15.7 if I supply USDC and R Ethereum, which is Rocket Pool Ethereum. The same thing for here. At any point, I can also click execute strategy here, state the amount of Ethereum I'm willing to commit, amount of worth. All right. Then I click execute. If I click execute now, my MetaMask will pop up and the transaction will be executed for me. All right. So that's one of the things this agent mode does for you. Their values, these immutable variables, their values will never change again. So they become constant. So we don't need to define them as a variable whose value will change in future. We know that they are constant because balancer V2 address will not change. So we can easily put it in as an immutable and we'll assess its value once and it remains like that. So yeah, we save a lot of gas like that because we are not storing them in the storage. All right. So the next thing is let's come here. The our tokens amounts. Let's define them. So I'm going to come up here. I'm going to define them up here. Now, just to refresh your memory, I'm going to press Command down and click iVault for you to see the interface again. Okay, flash down. You can see tokens. The type of it is array of ERC20 interface, and amount is unit 256 memo array. Yeah. So this is in bytes. That's why over here I'm defining an array here for tokens, and the length of the array is just a single. It's just one. It can only contain one element, and that will be in the first slot. All right, token 0. Then I'm passing a flash loan to it, flash loan token. Then the same thing for flash loan amount in. Now these two will come, they will be something we would have to pass in when we are calling trigger liquidation function. So let me just come here and define my flash token, which is going to be address, and my flash loan amount is going to come here as unit 256. All right, so the same thing has to be passed down to the internal function too, and where I am calling this internal function, I have to pass them in. There's still more parameters you're going to pass in. All right. Yeah. So the next one is this, our message. We need to encode it, and that's where the major work is. Now we need more parameters to pass in here. So I want you to see, we need to add the borrower address. So the address of the borrower we want to liquidate, the collateral address of his collateral, whether his collateral is Coinbase, Bitcoin, or Wrapped Ethereum, which token it is. Then the debt assets, the token he has borrowed. This is the address, all right? So over here, we are just going to come here and pass them in. Over here to pass that in. Pass this also in. So we're going to copy this 3 and we're going to paste them in here too. All right, so we've added more parameters because they are quite important. Let me know wonder of the topic. This encoded, these are a message. Let's just come here and define it. Let's stick with getting our flash loan from Balancer V2 before we do other things. So here, now the encoded message has to be in bytes. So bytes memory, this is how you define bytes in Solidity. Now we are sending empty message for now. Of course, we plan to put our swap and liquidation message inside here, but let's just take it like this for now. So on this side of things, requesting for flash loan, I think we are okay now. So we'll now come here, what we want, what we want to execute after getting the flash loan. That's what we are going to put inside here now. And the first thing is we need to ensure that anybody calling this function, this receive function, is the balancer vault. Nobody else can call this function except the balancer vault. As I said, this is where we call balancer vault, these vault contracts, and we request for flash loan. And in response, it will call this function receive flash loan for us. So we need to ensure that number one, it's that balancer vault that is calling it. So this is what this condition will do for us. It will revert if it's an unknown caller. Number two is to ensure that the flash loan, there's flash loan tokens. We are going to obviously request for only one token. So maybe Wrapped Ethereum, we are not going to ask for multiple tokens as flash loan. So it should be one. And the amount of the token we want, of course, the array also has to be one. Then the fee amount we are going to pay has to also be one. Now, of course, the fee, and that's why we are using Balancer V2, is the fee here will be 0 because it's free to collect flash loan. All right. Then if none of any of this is not as expected, it's going to revert this error. So I'm just going to copy this error now, and I'm going to come up here and define it as error. Yeah. So this is how you define error. You can define error as this, or you can also define it as this. All right. Although this is more gas efficient because here you are storing string on the blockchain. So this is more preferable. Let's include another important line here. And it's this line that after everything, we have to transfer the flash loan token that we borrowed. We'll transfer the amount back to the balancer vault. As you know about flash loan, you borrow it and you transfer it back in the same block within the same transaction. If you can't do that, you won't be able to take the flash loan in the first place. So the final line here would be for us to repay the amount we borrowed. So I need to define this repay amount. I'm going to come up here now and define our repay amount. And I need you to pay attention here. Repay amount is the sum of the flash loan amount we take and the fee amount. Again, the fee amount is going to be zero, but should they change the fees in future, so you want your contract to take care of that too. So that's what that's how we have to transfer. You can see we are calling transfer on ERC20 interface to transfer it back. All right. So we need to define this flash loan token too. Please don't forget to check out our website where you can explore our other services. Just go to syncedgesolutions.xyz. If you click bots tab here, it will take you to the page where our other bots are listed. For example, we have AI enhanced deck snipping bots V3, and this when you click details, you'll be able to see the video demo of this snipping bot. What it does for you is to watch Uniswap V3 and Aerodrome V2 pool for new tokens launch. And when new tokens are launched, it runs 10-point safety check on them to be sure that they are not honeypot tokens, they are not scam tokens. Before, it also uses AI to gauge the sentiment on Twitter before picking these tokens up. So when he buys the tokens based on your configured stop loss level and take profit levels, it will manage your position for you. You can configure as many take profit levels as you want. And yeah, it does that for you. For you not to be redundant, I'm just going to come here. This is already in ERC20 interface. So I'm just going to change the whole of this to this array because our flash loan token will be the only ERC20 in this array. So we will just call it like this directly and we'll transfer back whatever we have borrowed to the flash loan. I mean, back to the balancer vaults rather. Now with this, we should be able to request for flash loan, confirm the receipt. Let me just change the comment here because basically what we've done here is confirm the receipt of flash loan. Then let me delete this flash loan from balancer V2. Then the rest here we would have to do over here before we transfer it back. We need to execute swap and liquidation. That would be the next phase. And we also need to emit events here. Now you need to know that emitting events is quite important because every time you update state variables, you need to emit events. What you are doing is to log what has happened in your contract on the blockchain. So every time you emit events, this is registered on the blockchain. So should you change your front end in future, you'll be able to pull all the logs, the events you have emitted in the past. And so you could trace what has happened in the past. So it's a good practice. In fact, it was one of the best practices to always emit events once you make any state change. All right. So we need to emit events here, and we also need to emit events after this. Yeah, somewhere here too, to show that we have requested for flash loan. All right. So, but with what we have here now, it should be able to compile. So before we move to the next stage, which is here, so to obtain what we've done is to request and we have been able to repay the flash loan. So let's compile and see if it compiles. So I'm going to press Command J to bring up my terminal and I'm going to run forge build. That's how you compile this code. And if everything is good, all right, everything works well. We just have warnings that are showing that there are many variables we've defined and we have not used. So like this, address borrowers, borrower collateral, debt. Of course, we are going to use all of them and our user data. All right, so we can continue. Remember, I told you that all protocols are deployed smart contracts on the blockchain. And if we want to interact with deployed contracts, we need two things: ABI and the contract address. So we want to interact with Aave now for us to be able to liquidate bad loans. So here we have just come to Google and let's search for Aave V3 pool contract on base mainnet because that's what we want to interact with. Then so you have these options. So let's click this and it's going to take us to Basecamp. So this is the contract we're going to interact with. So if you come here and you click contracts here, you would see the code, the contract itself. All right. To summarize that, come to write as proxy and you see the functions you can call and interact with. All right. So we are quite we want to interact with this contract now. This function, liquidation call. You can see it accepts the collateral assets parameter, debt parameter. These are the things we need to pass in, right? There's another function we would also need to interact with, read as proxy. I just click read as proxy. If you come here now, we'll need to talk to this function, gets reserve, get user account data. This, all right? It takes the user, it takes the borrower, and we'll be able to get health factor from there. So that's what I want to quickly show you. So we are going to create interface from this now. Now I'm going to come here now and I'm going to create a folder. I just right clicked and I selected a folder, new folder. I'm going to name the folder interfaces. So all our interface, this is where we're going to be putting them. I'm going to also right click on the interface folder and create a new file inside it. I'm going to call it I contracts. So all the interfaces we need will be stored in this contract. All right. I contracts interface. All right. So over here, this is the interface for Aave pool that we'll be interacting with. You remember I showed you get user account data and it takes the user address. Then it returns all this for us. For us to liquidate bad loans, this is the function we are going to call. And it also takes all these parameters. All right. So feel free to pause the video and copy this down or just go to the contract on Basecamp and you can also generate, copy this down yourself. Now I'm going to come here. This should be contracts, not contracts. Okay. Now let's come back to our liquidation executor and we're going to import the interface we just defined inside iContract. So this is how we call it. Don't forget this iContract is in interfaces. This dot shows that in this current directory, just go in this current directory, you see this interfaces folder, then go inside it, you see iContract dot so far. All right. So yeah, then as we did before, over here, I'm going to create another immutable variable here, which will be Aave V3 pool. And I'm going to come to the constructor to initialize it. Okay, let's say, so we are going to pass address of Aave V3 pool in here. And we are going to assign the value to the immutable value to initialize it. All right. So with this, let's now come down here and call liquidation. So this is how we call liquidation, and I need you to just be patient and pay attention. So you can see the Aave V3 pool address we pass in here. So I wrap it with the interface. So this is the contract itself, the Aave V3 pool contract itself. So we call the function liquidation call on it. It takes collateral token, it takes the debt tokens, it takes the borrower we want to liquidate, and it takes the amount of debt we want to pay. And this it's false actually. So if you pay attention to when we checked the contract on Basecamp, this is for, it's outside the scope of this video. So we'll just keep it as false. Now we have a couple of challenges. Before we get to the challenges we have, you need to understand the purpose of this approve. All right. This liquidation call, what it does is to take the debt token, the amount of debt token from our contract to pay the debt of this person. No contract or no wallet can take any amount from your contract or your wallet except you give that contract approval to do so. Now, you remember that when we are liquidating, what we are doing is to pay the debt of this borrower. So we have to give approval to Aave V3 pool to take the debt token and this amount of debt token from our contract. Then, so that way we liquidate this borrower. And so once we've paid, because we've liquidated the borrower, we'll also be paid the collateral. The seized collateral of the borrower will be sent back to our contract. So we need to know the amount. So this is the balance of the collateral token, the same token we have before calling liquidation. And this is the balance after calling liquidation. So we do subtraction to know the amounts we receive. Now, all of these parameters, most of them we've not defined. So we need to define them. Now, as we are defining them, I need to introduce you to the two challenges we have. Now, the first challenge will come here. Now, we are going to be borrowing our flash loan. Our flash loan token will always be worth, and why it's going to be worth is that the liquidity is always available in Balancer V2 in worth. Of course, they could also have USDC, but it may not be as sufficient as USDC available in the Balancer V2 may not be enough as we want, but worth is always good. It's always available and in the right quantity. So our flash loan would always be worth. Now, that our collateral. Now, we cannot determine what the debt token, the debt the borrower has collected, the token it's in. So the borrower could have a debt that the collateral will be Coinbase Bitcoin, right? And is the debt token will be USDC. Now, our first step is we have to swap our flash loan token to USDC. Let me write this well. So we need to swap over here. Would have to swap flash loan token to debt to the debt asset. Debt asset. All right. So that's the first thing we have to do. Now, when we swap our worth, the flash loan token, to USDC, then we can go and pay. We have enough USDC to liquidate, to pay the debts of the borrower. Now, the challenge will now be after we have paid and we are given collateral. In this case, the collateral of the borrower is Coinbase Bitcoin. So we'll be given Coinbase Bitcoin and we need to pay back the flash loan. We need to pay it back in worth, right? So that means that we also need to come after here and swap the collateral token back to flash loan token, which is worth. essentially what we are doing is, if I come here now and just define where Coinbase Bitcoin, of course, is our collateral, and USDC is the debt asset. All right. So essentially what we are doing here is we are swapping our flash loan token worth we are swapping it to USDC, which is the debt asset. That's the first step. And here, what we are doing is to swap our collateral that must have been given to us back to worth. So then we'll have enough worth to pay this flash loan, to pay back this flash loan. All right. Now, this takes us to Uniswap V4 because we'll be using Uniswap V4 DEX for all of our swap. So you can see how important it is for the swap to take place. Now, another thing we need to also pay attention to is this function receive flash loan. It's a callback function for balancer V2, as I told you. So all these parameters, we cannot add more parameters to them because this has to be the function signature like this. So all the parameters we need for swap, we cannot add them here. What we can do is to put all those parameters inside this user data. All right. So that means we can only pass all those parameters in here when we request. At this point, when we request for flash loan, we'll put all of the things I have explained to you, we put them inside this. All the parameters needed, everything we need to do, we'll put them inside here. And when we get here, so when we get into this function, it will be sent as user data. We'll decode it and we'll perform everything here. So let's go to Uniswap V4 and let's talk about that. Then we will be able to implement it. Now here we are on Uniswap V4 documentation. So we are quickly going to review the implementation. We are going to review the concept here before we do the implementation so that when I'm calling some terms, you would know where I'm getting them from. So Uniswap V4 is a bit different from the previous DEXs like Uniswap V3 and V2. The major difference is that this pool manager contract you're seeing is where all the swap takes place. So in previous Uniswap versions, you would have a dedicated contract for example, wrapped Ethereum USDC. That's a pair. It will have its own contract. Then you have another contract for Bitcoin USDC for swapping them. So you have, for the number of pairs determines the number of smart contracts you have. These contracts are called pools. All right. Now, in the case of Uniswap V4, everything is contained. All the pairs are contained inside the same contract called pool manager. So that's where we'll be doing our interaction. And this is an example of how it's meant to be implemented. All right. Now, you can see two major functions we need to pay attention to. This execute swap function and this unlock callback function. So this execute swap, it's our contract. You can see it's external function. It's this function we can interact with, and it requires us to pass the parameter PoolKey. PoolKey is a struct. All right, so you'll see how we are going to implement that. So this PoolKey has the identity of the pool that we want to interact with. So this is where we are going to tell Uniswap V4 that we want to swap, we want to interact with wrapped Ethereum USDC pool. All right, so this PoolKey has it. Then this is the amount we want to swap. All right, then inside this function, we are going to call this pool manager. Now, when we call this pool manager, saying we want to swap, the pool manager will respond to us by calling this unlock callback function. So we need to implement this unlock callback function in our contract. Now, the first thing is when it calls, we need to ensure that it's the pool manager that is calling this function. We don't want anybody to call this function, all right, except the pool manager. Then after it calls, then we execute the swap. That's the way it works. So let's go inside this execute operation function and see how the swap is done. So I'm going to, all right, so we have it here now. Now, the first thing is it decodes the byte data we send in and it brings out our pool key. Again, as I said, it tells Uniswap V4 where we want to, the pool we are interested in doing the swap in, all right? Then the next thing is we need to call swap itself and say we want to swap, all right? And these are the parameters we need to pass in, these swap params. Now, swap params is also a struct on its own, which is defined in pool manager interface, and it takes these three parameters. Now, these three parameters just tells Uniswap V4 that the direction we are swapping to. All right. To break that down, now Uniswap V4 takes in a pool, there will always be base token and the other token. So if you have wrapped Ethereum USDC now, USDC will be the base token. If you have Bitcoin USDC now, USDC is the base token. All right. So how does it determine which will be the base token? It will compare the address of the two tokens, and the one with lower address is taken as the base token. So it's taken as 0, all right? The other token is taken as 1, all right? So if we are swapping from the base token to the other token, is taken as true, all right? And if we are swapping backward, this will be false, all right? So that would be 1 to 0, all right? Now, amount specified, this can be negative or positive. When it is negative, what we are telling Uniswap V4 is that these amounts means that we are interested in getting, in swapping, for example, 100 US dollars as our input, and based on the current price, it should tell us what the output will be in euros, for example, or in wrapped Ethereum, for example. All right. So if it is positive, it means that these amounts we are putting, it means that the output we are interested in getting 100 euros out as output. So it should tell us how many dollars we need to put in. All right. So all these you see when we start implementing it. All right. So after this, these two lines basically it just does the settlement, and yeah, everything is, these two lines just settles and takes and settles the swap. So yeah, and it returns the bytes here. So what we are going to do, we are going to copy this execute operation. Yeah, we are going to copy it and put it in our code. All right. So let's jump back. Now we've spent the last 5 to 10 minutes discussing about the concepts. So now let's implement. Let's get back to coding. All right, I'm going to press Command J here now to bring up my terminal. Let me just clean it with Command K. Now the first thing is we need to install Uniswap V4 contracts so that we can interact. We can import them into our code. So I'm installing Uniswap V4 now. I still have a couple of more Uniswap V4 contracts to install, to install and import into our code. All right, that is installed. Then we need to install this V4 periphery contracts too. Still going. Right, it's installed. Let me just drag this. Alright, then there's another one we need to install. This permit 2. I just press enter and it's going. We need to install Uniswap universal router. So it's going. By the way, I'm going to leave this command in the description of the video, and also the link to all the documents I've shown you. You'd see everything. So you'll be able to access all of these resources in the description of this video. Right, this has been installed. Then we need to install this V3 core. It's also going. Now we also need to install V2 core. Finally, we are going to install Open Zeppelin contract. It's going. Alright, so the installation has been completed. I'm going to do Command J again to hide the terminal. Now, all of the libraries we have installed, I'm going to come here and import all of them. It'll be quite helpful for what we have. Now, we are having this error because I have not defined them in the remapping text. So we are going to come here and define all of them. Over here, I'm going to paste all of them here. So I open Zeppelin, the V4 core and V4 periphery, the permit to all of these libraries. So let's come back here. Yeah, they've all disappeared. Now our contract has to inherit this interface, so I'll come here and include it here. This unlock callback, as we saw earlier in Uniswap V4, so we need to inherit it like this. Now I'm going to come down here. I'm going to define these two structs. Now the first one is liquidation params. What is going to help us to do is to bundle all liquidation parameters through the flash loan. So everything we need to encode here, this will help us to bundle them together. You see how we are going to use it. Then these are swap data, is for us to pass inside the execution operation inside when we call unlock on pool manager. So you also see how we'll pass all these inside. There's something I forgot here. So you can see we are passing the borrower here. We need to check the health factor of the borrower. So by calling this get user accounts data on Aave Pool3 contract, then we'll get the health factor. If the health factor, if it's greater than 1, this is 1 times 10 raised to the power 18. This is just precision. All right. So if it's greater than 1, that means that the loan is not liquidatable. So we are going to revert. So before we waste gas, we are just going to revert this error. So I'm just going to come up here and define the error. All right. And again, we are also emitting events. All right. So we are going to emit this event. This is CRE, that's Chainlink Runtime Environment, liquidation triggered. So once this is performed, then we can emit the event showing that this has been triggered. Now, don't get confused because we are emitting events before executing this internal function. All right. So if this internal function fail at any point, if it reverts, all right, the fact that we have emitted events, the state, there's no partial state in blockchain, so everything will be reverted. Every code that has been executed so far will be reverted, so this will still not be on the blockchain. All right, so it doesn't make any difference whether we put it below or above. All right, so I'm going to come here and go up, copy this, then somewhere here, events, we are going to be defining our events here. So this event takes address of the borrower and takes our own address, liquidator. Now I've added the keyword index there. When you put index, it means that you can search through your events based on the values of these borrowers and the value of this caller. All right, that's the point of this indexed. All right, so let's now come back here. Yeah, okay, these are internal function. Now, don't forget what we are working on is to get encode the right message inside here that will do our swap and liquidation for us. So I'm going to come up here, and the first thing we are going to have is this. So we are going to examine the flash loan token and the debt assets we want to swap. Which one has a lower address between the two, so that we'll know the one that will have, that will be our T0 token, our base token on Uniswap V4, and the other token, so T0 and T1, as we discussed earlier. You remember our 0 for 1, that variable, it's here. So I'm going to just comment it and write 0 for 1. Right, so we said it talks about, it tells Uniswap V4 the direction we are swapping to. If our flash loan token is the base token, this 0 for 1 will be true, otherwise it will be false. All right, so all these parameters will be included in our PoolKey. You remember PoolKey that I also showed you on Uniswap V4. All right, so this is the struct, and this is how we are going to define it. It takes currency 0 that we wrap around the address of token 0. It takes currency 1. We are going to wrap it around C1 token, the other token. Then again, we need to specify this flash debt swap fee. Now, I'm going to, before I explain what this means, will just come here and add 2 parameters more. So those 2 parameters are the swap fee for flash to debt asset swap and collateral to flash loan swap. I'm going to do the same thing here too. Okay, so I've added that to the 2 of them, and because I've added it here, I need to add to this and this. So please, you can pause the video and add this also to your code. Now, to explain this, I told you if we are swapping wrapped Ethereum USDC, there will be pool for that. If we are swapping Coinbase Bitcoin USDC, there will be pool for that. All of these pools are inside the pool manager. Now, there are also pools inside each pair. So what I mean by that is, wrapped Ethereum USDC will have a pool that charges you 100 basis points in fees if you swap in it. There will also be another pool that charges you 200 basis points, 500 basis points, 1000 basis points. The highest is 10,000 basis points. That's about, I think that's 1% when you swap on each of those pool. Now, of course, the main thing is you would always want to swap on the pool with the lowest fees, but the problem is it may not have sufficient liquidity for your swap. So you need to check those pools and check for the one with sufficient liquidity. So we need to specify where we want to swap our flash loan to debt assets, and this one is where we are going to swap our collateral to flash loan token. So that's why. Now, the next one is we need to define this. And again, I'll just come down here. It's going to be an internal function. It's an helper that converts the basis point to the actual tick spacing on Uniswap V4. So if the fee we enter is not a valid one, it's going to revert. So let me define this error up here. All right. Now you can see the agents tab here that we didn't have before. And what we have here, before you be able to see all of this, you must have deployed your own agent bots. So what does this do? It helps you to watch over your health factor. It watches over your position for you. And if your health factor drops below a position you have configured, and that you must have configured it over here. I'm using 1.25 for my own. So if it drops below 1.25, it's going to automatically close my position for me. All right. So the agent votes, this is it's a subscription based and it's fully on chain. Besides guarding your position, it also helps you to deploy different strategy based on your sentiment of the market. So a good example is that if you come to this strategy intent panel here, you can tell you can see whether you are delta neutral or you are bullish on the market or you think the market will go down, which is delta short. So now I'm feeling bearish. I want to short the market. So if I click here now and I say my target APY, because that's one of the good things about pivot bots. Instead of paying funding rates on other trading platform, with pivot bots, you'll be earning yield on your open position, as you saw earlier. So let's say my target is maybe 50%. All right. Delta shots. Let's say my risk tolerance is moderate, and I click analyze. So you can see the strategy is giving me. So I can supply USDC and borrow VF against it, and I use about 3.5x leverage and 15.8 APY. I'll get up to 15.8% APY. All right. So at this point, so the top three strategy I can deploy is going to give me there's 15.7 if I supply USDC and R Ethereum, which is Rocket Pool Ethereum. The same thing for here. At any point, I can also click execute strategy here, state the amount of Ethereum I'm willing to commit, amount of worth. All right. Then I click execute. If I click execute now, my MetaMask will pop up and the transaction will be executed for me. All right. So that's one of the things this agent mode does for you. Now let's scroll down back here. So we've been able to define the pool key when we want to swapping flash loan to debt assets. Don't forget, we also need to swap collateral assets to flash loan token. All right. Now, the final one I didn't talk about is this hooks. Now, this it's outside the scope of this video, but again, we are not building anything related to hooks on Uniswap V4. That's why the address here is 0. All right. So what we've done here for swapping flash loan token to debt asset, we have to do the same thing for swapping uh, collateral assets to flash loan token. So I'm going to come here. I'm going to write all of this. So please feel free to pause. So again, as we started here, we need to find the base token by comparing the collateral assets to flash loan token. Then whichever one is smaller is the base token. So if our collateral, you remember our 0 for 1, let me just include the comment here. And by the way, if you don't know, once you see double slash, it means comments in Solidity. All right. So if our collateral asset is the base token T0, then this our 0 for 1 will be true, otherwise it will be false. All right. So again, we have the same pool key. You have to do pool key for this one too. And this is our token 0 here, token 1 wrapped around currency. Then you remember the swap fee we passed in here. We passed it in. Then again, we'll convert our swap fee to tick spacing, and we are not building any hooks. All right. Now, all of these, we'll have to pass them into, you remember the struct we defined up here, liquidation params. So we have to create an instance of this struct, which is params, and it takes the collateral assets. This is the value, collateral assets, the debt assets, the borrower, the flash loan token, the flash loan amount, the pool keys we have defined. It takes the two of them. All right. And our 0 for 1 too. It also takes our 0 for 1. So these params is what I'm going to encode now, and it will be what we are going to pass inside. These are encoded. So these encoded, as I said earlier, will be passed back to us as our user data. All right. Now, there's a major security vulnerability here that we need to pay attention to, and it's called flash loan spoofing. Now, this function is receive flash loan function that I told you that our balancer V2 will call. Now, with this check here, it ensures that only balancer V2 can call this function. But balancer V2 can be called by anybody, even though this function can only be called by balancer V2. So someone else can call balancer V2, include any random data in it, and with that data, balancer V2 will call our own function here and pass that data in, and that way the money on your contract can be stolen. So we need to ensure that it is exactly the message we encode here that balancer V2 is sending back to us here. So this encoded here is exactly equals to this. All right. So for that, I'm going to come here, up here, and define a storage variable. So it's going to be S flash loan payload. All right. So the payload here will initialize it just after the params here. It will take the value, so we'll save the message here. Now we are going to come here now and compare what we have. All right. So our user data here, number one, we are going, this line checks whether it's empty. So you can see the length, because it's going to be sent in bytes. If the length is 0, that means it's empty. We are going to revert with this error. So let me define this error up here. All right, while I'm here, let me define the second error too. All right, so the two error, we've defined them. I didn't define this correctly. So it's meant to be this. All right, so now this is how we compare strings bytes in Solidity. So you hash the strings, this user data, with the one we stored when we were requesting for flash loan here. So if they are the same hash, that means yeah, the execution can continue. But if they are different, it's going to revert with this error. All right. Then after that, we need to reset our variable to empty again, so that when next you come back again, this is empty, and we can continue like that. All right. Now we need to now decode the user data. So this user data we sent in, we encoded it. We are going to call ABI decode the user data, and don't forget the data type, the structs we use is liquidation params up here. This struct, that's what we'll use. We'll pass it in to tell it that this user data is expected to be in this data format. Then it will be passed into our variable, which is also of type liquidation params. So this will help us to decode it back to how we can use it. Now we can now come down here and deconstruct this P, these liquidation params, and use them. All right. So we have a flash loan token. You can see most of these things we have ended up defining them here. All right. Now we did not define this error. I'm going to copy it and come here and define the error here. Yeah. Let's come back here. Now let's define this variable debt to cover. I'm going to come up here just below this immutable values. In fact, these and these are meant to be together. So it will be below these immutable values. So debt to cover will be maximum integer possible, making it as large as possible. So over here, the liquidation is going to take here this amount from our wallet. Now, because we approve the large, we state the amount to be a very large integer value, doesn't mean that this transaction will take this value. It just means that it has the power to take as much as this, but it will take exactly the amount it requires. So if you go through Aave V3 documentation, you see that this will be calculated by Aave by itself here, and it's going to take the exact amount this borrower is owing. Let's do our first swap, which is to swap our flash loan token to whatever the debt asset is. So I'm going to come here and put this code here. So basically what this code does, I've just commented it out because, okay, before I comment it out, let me just explain it. And now you see that we are testing if our flash loan token is the same with our debt asset. If it is the same, so wrapped Ethereum, we don't need to swap anymore because we have the right token to liquidate the borrower. But if we don't have the right token to liquidate the borrower, then we need to swap. So execute V swap. This is an internal function that will help us to swap that we need to call. So I need to create this function. So that's why I'm going to comment this out. So it's going to do that, and whatever comes out of it will be our debt balance. Debt balance is the token we have to pay the debt. All right. So if there's no swap, then whatever the flash loan we are getting is will be the debt tokens, the amount we want to use to liquidate this. So because we need to swap, I'm going to comment this out for now. Then after we finish writing this function, I will uncomment it. Jesus. Now we're going to come down here and do the same thing. So after the liquidation, you must have received the collateral at this point. Am I in the right place? No. It should be here. Yeah. So after the liquidation here, then we must have received this collateral. So we need to also swap our collateral to wrapped Ethereum, which is the flash loan token. So again, we'll go call this execute V4 swap for swapping. So I'm still also going to comment it out for now. Now, this is our execute V4 swap function. Of course, it's an internal function, which is a wrapper for another internal function execute V4 swap with minimum out. So if you look at these two functions, they look the same, but they have one parameter that differentiates them. This one takes minimum amount out. This does not take it. In fact, we get it here. All right. And I'm going to talk about that. But basically, this is where the swap takes place, because in this second executes V4 swap minimum out, that's where we call pool manager to initiate the swap. We have to form our swap data. We'll encode it here, and it takes, you can see this function, it takes our pool key, just like execute V4 swap. It also takes our pool key, and we have said the pool key tells Uniswap V4 what pool we are going to be doing the swap in. So they both take our token in, token out, the amounts we want to swap, and our 0 for 1. All right. Now, this minimum amount out that we are going to compute with this function, we are yet to define that, and we're going to define that. Now, this is a threshold, all right? And let me tell you how important this is. Let's say we want to swap worth for USDC, and the current price on Uniswap is one worth goes for 2000 USDC. Now, once we initiate the swap, we don't have control over it anymore, because as at the time that the swap is being executed, the price can move, and it can change from $2,000 to as low as any price. In fact, it could be $1,000. All right. So, but with this minimum amount out, we are going to tell Uniswap V4 that if the token is going to give us, if it's less than 1,990, for example, we are no longer interested in the transaction. It should cancel the transaction. So this minimum amount out help us tell Uniswap V4 the minimum amount of token we are willing to take in exchange for our one worth. All right. So when we define this compute minimum amount out, you would see we'll pass our slippage in, and I'm going to explain that. And most importantly, we are going to call Chainlink price feed inside this in order to compute minimum amount out. All right. So let's move on. Before I wander off, let's complete this first. You remember I said when we call unlock on pool manager will respond by calling back unlock callback on in our contract. So over here, let's define that unlock callback. Told you we're going to copy it from Uniswap V4 documentation. So this is the callback function. We call pool manager, it responds by calling this back. This data we encode, that's the swap data, what we want to swap that we are passing in. So the first thing is for us to check that it's actually the pool manager that is calling back. So there are some parameters I've not defined here, like the address of the pool manager. So the first thing is we need to ensure that it's only pool manager that can call this function. Then we decode the data we pass in. It's going to decode that. After that is our amount specified. All right. Now you see we are using Safecast library here. Safecast library is a library on OpenZeppelin. Earlier here, you can see we imported it from OpenZeppelin. And what it does for us is to ensure that when we are changing from one data type to another, the information, the data itself does not get corrupted, all right, in the process. So that's it. You remember amount specified can be positive or negative, depending on whether you want to do swap exact input to output or exact output to input, as I specified earlier. So this is helping us to tell Uniswap that this is the amount we have in input. It should give us as much as possible in output token. All right. And the swap will take place here as we saw it. So I'm just showing you this to remind you of what we discussed when we were looking at Uniswap V4 documentation. All right. Then after this swap, the actual taking of our token and giving us a new token takes place here. All right. Then all we need to care about is what's the balance of our token out before. This is after the swap. Before the swap, this is the balance before. So we are going to compare. So if the difference, what we received, is less than our minimum amount out, you remember the minimum amount out we are working, we are going to calculate from here. The minimum amount we are willing to accept for our swap. If it's less than it, it's going to revert it because it's less than what we want. It will cancel the swap for us. But we want it to be at least equal or higher. All right. So let's define some of the parameters here that are giving us headache, like this error now. Okay. There's another error that was messing around earlier. Okay. Right. As we proceed, I will find the error. I'm going to come up here and I'm going to define another immutable value, immutable variable for our pool manager. That's Uniswap pool manager. We are going to pass an address in to the constructor. Here's constructor here for the pool manager. That's it. And that will help us to initialize it here. Yes. So all this noise should be suppressed now. Yeah, it's been suppressed because we've initialized and assigned value to our pool manager. Here is the error that was hiding before. So I'm going to come up here and define it. Error only pool manager. Over here, I'm going to come down here and define this compute mean amounts internal function. So you can see we have the public view of it. A function that is marked public means that it can be called by other functions inside this contract and can also be called from contracts outside of this contract, or it can be called by a wallet, a user outside this contract. So it's available everywhere. All right. So I'm doing that. You'd see how we'll use it to be able to compute price for any given token before we do the swap. All right. So it takes our token in, token out, amount of the token we want to swap, then slippage. All right. I've not defined slippage, but I will do that. Then it's a wrapper for this internal function. This internal function is what help us with this our Chainlink feed. All right. This Chainlink feed is a mapping, and I think, okay, before I proceed to explain it further, let me define what each of them mean. All right. Then I'll come back and explain them. I'm going to come up here now because these are mappings that we need to define. So I'm going to come up here and explain what mapping a special data type in Solidity is. So I can define it here. Now this Chainlink feed, what it does is it maps the address of a token or address to the address of its price on Chainlink. All right. So every time we have something like this now, for example, here we say Chainlink swap feed token in. So if the token in is wrapped Ethereum, so this is going to return the address of wrapped Ethereum USDC to this feed. Right? If we do Chainlink swap feed token out, for example, token out, if it's USDC, this will return the address of USDC USD on Chainlink to us. Now, these two mapping, they're essentially the same thing. They are going to take the same value. But I had to use two variables for the same thing because it will help us when we are testing, when we are crashing price. So that's why I have two feed doing the same thing. In production, you should basically what they are doing is to this is checking whether we've set the swap feed token in address. If we have set it, it's going to return the address, the Chainlink address for this token in. It's going to return it to this feed in. If we have not set it, it's going to return the one for the Chainlink feed here. The same thing for the feed out. The token out, if we have set swap feed token out address, is going to use it. Otherwise, it's going to use Chainlink feed token out address. So here we have the address of where to ask for the price of our token in and token out. So with that address, we'll call the Chainlink aggregator for the price, and it's going to return it to us. So it will return all other things with it, but we are only interested in price in and price out. All right. Then if the price is 0, we are going to revert. Let me define this error up here too. We're going to revert. All right. So after that, we are also going to call the token decimal. All right. Now token decimals which we have we have written here. Just 1 second and I'm going to explain that. So now over here, I think let me just show this side of the code so that you get the full picture of the code so that you can take everything down. All right. Now, after again, I'll still define the chain link aggregator. Well, let's come to this token decimal. Every token has its own decimal. And what that means is, for example, US dollars. US dollars can be subdivided into 100 units. So 1 US dollars is 100 cents. In pounds, 100 pence is 1 pound. And for Nigerians, 100 kobo is 1 naira. So what that means is that 1 US dollars can be subdivided to 10 raised to power 2. So the token decimal in this case will be 2. All right. Uh, in the case of tokens, the most common tokens, they can be subdivided into 10 raised to power 18. So the token decimal for wrapped Ethereum is 18, 10 raised to power 18. USDC is 10 raised to power 6. It can be subdivided into 10 raised to power 6. Coinbase Bitcoin is 8, 10 raised to power 8. Then, now other tokens that we might be dealing with, even if we don't have them, if we call decimals, they all have, since they are standard ERC20 tokens, they have this function on them, decimals that we can call, and it's going to return a number like this for us to know the number of decimals they have. So yeah, we'll just call that to know the number of decimals. All right. Yeah, so that's the whole point of decimals, because we are going to use that to calculate our minimum amount out that we need. Now, this is how we calculate our amount in, minimum amount out rather. So you can see numerator divided by denominator. And the numerator is the price of the token in, the amount in multiplied by the price of the token in. Now, we have to take this slippage from 10,000. This slippage is in basis points. Basis points means that you multiply the percentage value of this slippage by 100. All right. So the maximum you can have, which is 100%, is 10,000. Now, what slippage does is it tells Uniswap V4 that we are willing to take, if the slippage is 1%, we are willing to take a price less than 1% of the amount we are supposed to get. So that means that we are willing to take 99% of the actual amount. If we set it at 0.5%, it means we are willing to take 99.5% of the actual amount. And if we set it at 0.1%, it means we are willing to take 99.9%. So whatever that is, our slippage value, if it's 1%, 0.5, 0.1, whatever it is, we'll take it from 10,000, use it to multiply the price and amount in, and again, use it to multiply the actual decimal for the token out. Then again, we'll follow this for our denominator too. All right, then we'll divide, find the ratio. That would be the amount we are going to return as our minimum amount out. So this Chainlink interface that we are calling to get the price of the token in and price of token out, we're going to come here to define it. It's an interface that we are going to define here. I'm going to paste it here. All right. So these are the functions we'll be calling inside the Chainlink aggregator. So I'm going to import it now. Come here. Since it's coming from the iContract file, which is the same thing as here as I have a pool. So I'm going to just put it here. All right. And that ensures, yeah, you can see that the code can find it now. Now up here, we need to define our slippage. All right. So I'm going to scroll up here. It's just going to be some constants here. I'm going to include it here. Now, when we are setting our slippage, because we'll make it something we can change in future, the minimum value must not be less than 5, and the maximum must not be higher than 10%. So you don't want your slippage to be as high as 10% actually, because that's you giving money to front running bots, right? But we'll stay, our default value will be 50. 50 corresponds to 0.5%. So yeah, that will be our default value. All right. So I need to assign that default value to the slippage BPS. Over here, we are going to do that just underneath them here. Yes. So the default value, our slippage BPS takes it. Now, so since we have defined those functions, we can now uncomment this. We have execute V4 swap, and it takes our PoolKey flashloan token as token in. So it swaps it to our USDC for us. Then the debt balance will be the tokens we receive. All right. Then we can do the same here too. All right. So this swaps our collateral for us. Now here, when we are emitting events, before that, we need to, number one, we need to get our profit. So this will be the flash loan tokens left. Yes. I'm going to write this function. It's an internal function that if there is any flash loan token left, it's going to transfer it for us. Debt token left is going to transfer it for us. Collateral token in this contract is going to transfer it for us, just to ensure that we don't keep any token in this contract. Then we are going to emit this event. So before I define that, there's something we need to do together here. All right. Over here, it's quite important. Now, at this point, you understand that we only have collateral tokens and some debt assets left at this point, because this liquidation call would have taken our debt tokens, but we don't know how much of it has taken. All right. So there must be some dust left, and those dusts are not useful for us except they are in flash token. So we are going to swap those dusts, swap dust of debt assets back to the flash token. Flash token. Alright, flash loan token. So I'm going to come here now, and we're going to conduct the swap here. So the excess will be the debt token in the contract at this point after the liquidation. Then if it's more than 0, then we are going to swap it back. Now the minimum amount, since it's dust, we can use a very small value here and say 1. All right. Well, some others prefer to also compute the minimum amount as before. So whichever one you want. That's why I just commented it out here and just put 1. All right. It's dust recovery. Then we have our 0 for 1 again. All right. Let's define this event first before we do the sweep or function. So I'm coming to where we have our event here. All right. I'm going to define it here. Borrower is indexed data sets, collateral, date covered, profit. All right. So I'm going to come down here to define however you like. You can arrange the functions. So if you go through the documentation of Solidity, you see the standard way of arranging them. All right. I think the public and the external functions come first, internal, private, and so the sweep all calls the three tokens, debts token, collateral tokens, and transfer whatever their balance is, transfers it to our wallet. The one for the flash loan returns our profit, because our profit will always be in flash loan token. Let's define all these missing parameters. I'm just going to come up here for those tokens. We have the Ethereum, USDC, and Coinbase Bitcoin. Okay, they will also be immutable too. All right, and we are going to pass them in from the constructor as always. Yeah. All right. So over here, you should have them. All right. So we've initialized these 3 tokens here. Now we've not defined our owner variable, so you can see we still have owner error here. So let's define this owner variable. It will be our address. And so in this constructor here, let me just put the owner here. Okay, so what it does is msg.sender means whoever deploys this contract will be the owner. His address will be stored as the owner. Again, since the owner would not change, you can come here and declare the variable as immutable. All right, so no more error, but there are a few other things we need to do. Now I'm going to set another address here. I'm going to call that address forwarder. All right, now this forwarder address is the address of Chainlink Runtime Environment that will be calling this function for us once there is opportunity. So we need to store that address. Now we need to protect our external and public functions. Protect them in the sense that restricting the address that can call them. As it is now, these are trigger liquidation function can be called by anybody, which is not what we want. All right, so over here, because of that, we are going to define 2 modifiers. The first one, and basically modifiers are just small, they are just codes that you use over and over again in different functions. So in order to avoid repeating them, you just put them inside modifier, and you see how we're going to use them. So so what this does, let me just define this error up here. Error Then, so this ensures that any function we put only owner on, anybody that calls that function, it checks the address of the caller, and if that address is not the owner, it's going to revert. If it's the owner, the code in the function will be executed. The same thing for this modifier too. This one is checking that you, the caller, are either the owner or you're the forwarder, right? Otherwise, it will be reverted. Now we need this modifier here for this tree. Yeah, we need it on this function because this trigger liquidation, this function, this modifier allow us to call it, or the forwarder for automation can also call it. Now let's define some admin functions here, and we have the right modifiers now, so you can see them. All right, these are admin functions. The admin functions because only owner can call them. You can see the modifier here, only owner can call them. All right, now if you notice, let's start with the one you're used to, the slippage basis point. In future, we may want to change the slippage from the current default value, which is 0.5% to 0.1%, any amount at all that we want. This is how we'll just pass it in here. It's going to check that we are between the minimum and the maximum value. All right, because if your slippage is 0, that means that every swap you try to perform will fail, because that means you want the exact amount at the price is going for. You don't want any deviation at all, which is impossible. And if it is maximum 10%, you'll be losing a whole lot on every slip. So you don't want it to be above this. All right, then we'll set it and emit we'll emit events. We need to define the events up there. Then these are Chainlink feed. You remember this Chainlink feed, the swap feed we defined up here. All right, so this allows us to add more, or for new assets, add, if Chainlink decides to add more price, more feed for new tokens. So we also be able to add that to our contracts too. The first thing is to check for 0 address, because we don't want the feed or the assets address to be 0. So after that, we'll take that in, we'll pass it into our mapping and emit this event. So let me come up here and define the error too. All right, no 0 address. Then after that, we also, okay, this does the two of them do the same thing. Okay, feed already set. If the feed has been set already here, it's going to revert. So let me come up here and define the error again. Please feel free, make sure you pause and you code along with me. Pause this code so that you can see very well. Pause the video so that you can see the code very well and you get them down. Then this is our watch list. We've now written this contract. When we write it, we'll be able to save the address here too. This is the interface of the watch list. I'm going to bring that in. Then I need to define this too and emit events. We are going to do that now. All right, so let's come up here. These are all the events. Yeah. Now we need to import this. Now, since we have now written our liquidation watchlist contract, it's best I just comment this out until we write it. Alright. Yeah, so no more error. I think with this we have completed this contract. Then we'll move on to the next contract. Please don't forget to check out our website where you can explore our other services. Just go to syncedgesolutions.xyz. If you click bots, tab here, it will take you to the page where our other bots are listed. For example, we have AI enhanced deck snipping bots V3, and this when you click details, you'll be able to see the video demo of this snipping bot. What it does for you is to watch Uniswap V3 and Aerodrome V2 pool for new tokens launch. And when new tokens are launched, it runs 10-point safety check on them to be sure that they are not honeypot tokens, they are not scam tokens. Before, it also uses AI to gauge the sentiment on Twitter before picking these tokens up. So when he buys the tokens based on your configured stop loss level and take profit levels, it will manage your position for you. You can configure as many take profit levels as you want. And yeah, it does that for you. If you have been coding along so far, you're doing very great. If there are places that you didn't get, just go back and rewatch. It's all part of the learning phase. And if you have not been coding along, it's never too late to open your laptop, open your PC, and code along. That's how you develop the muscle memory. All right. So it's quite important to show you what we've done so far on the architecture side of things. So far, we've written these contracts and we've incorporated Aave V3, where that's where we'll be and we've been or we will be liquidating bad loans. We have integrated Uniswap V4 and Balancer V2, and we've also incorporated Chainlink price feed here to help our Uniswap V4. So the next step is liquidation watchlist smart contract. That's what we want to write now before we move to the automation phase. Now let's come here, and in this folder, this source folder, I'm going to right click and select new file to create new file for our new contract liquidation watchlist dot so. That will be the contract. As usual, to start every contract, we start with the license and the solidity version we want to use for the contract. Then we write the contract itself. It starts with the keyword contract and the name of our contract. All right. Now, as before, let's now write our to do. The first thing is this watch list is going to be storing array of our borrowers. All right. So number one, we need the following functionalities. The first one is should be able to help us to update the borrower borrowers list, which includes adding and removing. Yeah. Number two is should also be able to we should be able to check get all borrowers all the borrowers, check if a borrower is in the list, get the length, get the number of borrowers, not amount, number of borrowers. All right. So basically, these are the things we want to do. So basically, it's us dealing with an array of borrowers, and in Solidity, there's a library that helps us to do it perfectly well. And it's this open Zeppelin library called EnumerableSet. All right. So this library helps us to it ensures that we can easily add and remove. In fact, our complexity time is constant time. So our big O is one actually. So especially it's useful in areas in which you don't care about the arrangement of the position of the elements in an array. It can change. So you can easily use this library there. Now let's import this library into our code. That was a mistake here over here. So this is how you import a library using enumerable. Oh, that was okay. Using enumerable sets for this. Yeah. So let's define our constructor. I'll just come down here. Constructor, that's the first function that will get executed at deployment and only at deployment. All right, we are not passing anything in. Now we need an array in quotes where we'll store the list of our borrowers in our watch list. So this is how we are going to define it. Instead of defining it as this borrowers variable as array, we are using this library that we defined, and you will see how it's going to help us. Now, as we have said here, number one, we need a function to help us to add and remove borrowers in this array or the list, these borrowers. So that's this updates watch list. It takes our address array that we want to add. It also takes array of addresses that we want to remove from the existing list. All right. So we'll just loop through them one after the other. This is for adding. We need to ensure that there's no zero address there. Then we add. Now you can see if it was array, we will be using push here, but because we are using this library, this keyword add is available to us, so we can easily add and increase the counts. All right. Now to remove, if it was normal array, and this is where this library is quite important. If it was normal array, we would have to loop through all the elements in these borrowers to find the one corresponding to what we want to remove. But this remove is available to us in this library, and even the big O for this, it's one. So it does it easily, and it's quite cheap. We don't need to be looping every time. So that's why this is quite good. Then we'll emit events. So this event, let's define it up. Yeah, as I said earlier, it's a good practice to always emit events once you make changes to the storage. All right. So we are indexing. We can find this event by this update by, and yeah, whoever updates this will still have to restrict those that can call this update watch list, because we don't want anyone to call it. We just want to be the only one calling it. All right. This probably in fact, it's the most complicated function we are going to write in this contract. Before we move on to the rest, I want us to pay attention to this call data here. We have the option of also using memory keyword here instead of call data, but call data is quite cheap. So it's a way to save gas. That's one. Number two, because what we are loading here, what we are receiving, we are not manipulating it much. We are just reading it and storing it. So we can use call data for external function. All right. So yeah, that's why we are using call data. We can now move on to the rest. Now for 2, 3, 4, they are view functions. So let's just come down here and define them. So view functions are functions that just read from the storage of the contract. They are not storing anything. They are not making changes to the memory. All right. So the first one is get all. This returns all the values in these borrowers. So it returns it as array, an array of addresses. Then get count tells us the length of the watch list we have. Um, Contains, if we want to check if a borrower is in the list, so this one does it for us. So you can see how useful this library is. All right. Then lastly, get the position a particular, returns the borrower address at a particular position in the array. All right. So before we say we are finished here, we need to add access control to this function. So I'm just going to come up here and I'm going to create two modifiers. One is for owner, the other is for updater. Let me come up here and define these two variables, owner and updater. Owner will it's immutable because we are just going to pass it in here. Whoever deploys this function, whoever deploys this contract will be the owner and is not going to change. All right. But updater, of course, we'll be able to change it in future. But at inception, we want whoever deploys this contract, which will be us, to be the updater too. All right. I need to define these errors. I'm going to come here, down here. I'm going to define these two errors. Okay. Now we have this modifier only updater that we can use as access control to restrict this function. So whoever calls, if anybody calls this function, this modifier will execute and check if the caller is the updater, if he has right to call this function to update it. All right. If he doesn't, it's going to just revert unauthorized. Now we want to be able to change this updater in future. That's why it's not an immutable variable. The owner we cannot change, but updater address we want to be able to change it. So because of that, we are going to write this function set updater. We'll put a new updater there. Then we'll need to be sure that it's not a zero address. Then we are going to set the updater variable to the new address and emit this function. We need to define that function. Now, to change the updater, we want to be the only one to do that. So I have included the only owner modifier. Finally, we can come here. I hope you can see the screen better now. To emit updater changed event. All right. So if I went quite fast, I am going to, so you can pause and get this down. So we finished this contract. So let's come back to this liquidation executor contract. You remember this function set watch list that we commented out before because we hadn't written our liquidation watch list contract. We can now uncomment it. Now that we've uncommented it, you can see we need to import this interface for this liquidation watch list contract. So we are going to come to this interface and create interface for it. We just need to list, you can see we define it with interface keyword and the name of the interface, and we need to list all the external and public functions. We need to list them here. So you can see the external functions, all of them have been included there because we want them callable. So once we've done that, let's come back here. I'm just going to copy the name here and come back to this contract and include it among the interface we have imported. and that ensures that this one is complete. Yes. Now we've finished writing the two contracts, and the first thing is for us to compile, and let's see if they both compile. Sorry, I'm going to run forge build to compile the two contracts. Oh, now we have an error here, so I'm just going to press command and click. Let me reduce this. It's saying we have not defined this particular variable, so I'm going to come up here and define it. Should be somewhere here. Okay, yeah. So let's bring command J brings up our terminal. Command K cleans the terminal. Then I can press up to bring up the command again. Forge build, enter, and let's see if it goes now. All right, we still have something else here. Let's read the error together. Stack too deep. Try compiling with this. All right. So what this is basically telling us is, if we come here, let me just minimize this with command J. It's saying that this particular function we've written is having more than 16 variables at a time in the memory or the stack. Yeah. So that's why, because this particular compiler cannot take more than 16 variables on the stack at the same time. So, but there is a latest compiler that can handle that. So what we are going to do is to come to this foundry.toml file. We are going to direct it to the latest compiler, which is IR here, set it to true, and that would clear that error for us. Optimizer just make sure that our contract is gas efficient for up to 20,000 calls in the lifetime of the contract. All right, so it also further makes our contract gas efficient, although we'll be paying more for deployment. All right, so if I had made this one now 200, deployment of my contract will be a lot cheaper now, but the contract will only be gas efficient for 200 times in its lifetime when it's called. But let's play around with 20,000. All right, let's bring back the terminal. Command J and command K clears it up. So forge build again. Let's see. And it seems to be going now, and we only have warnings. It has compiled. All right, that means we did well. All right.